Thank you for attending the webinar. I am Danilo Coll, the European Product Manager of TrueLoad for Engine-Soft. And I am very proud to introduce you Dr. Timothy Hunter, the President and the Founder of Wolf Star Technologies. Okay, in this webinar, we will show you some real-world examples and how to break the cycle of failure in your engineering design. Okay, now I leave the word to Tim Hunter to continue with the webinar.
Okay, thank you, Danilo. Let me just get my screen sharing going here.
Okay.
Thank you, Danilo.
Okay, thank you, Tim.
So thank you, everyone, for joining us today for this webinar. Again, the webinar today is TrueLoad for Transportation Products, Break the Cycle of Failure. And in this webinar today, hope to show you several real-world examples that we've done, showing the power of the TrueLoad tool for understanding your product loading and how it can help you avoid failures. So here we go. So the products from Wolf Star Technology are quite simply, their flagship product here is TrueLoad. And TrueLoad basically turns components into load transducers. What we do is we have our users put unit load cases on their FEA models, and then we'll query the FEA model for optimal strain gauge placement. And then once the users find the optimal strain gauge placement, we extract a correlation matrix that relates load to strain response. Then our users will place strain gauges on the physical parts, measure strains in their operating conditions, and then we back calculate the operating loads from those measured strains. We're basically making load transducers is really what we're doing. We're turning your parts into a multi-degree freedom load transducer. The second product from Wolf Star Technologies is a product we call TrueQSE. QSE stands for quasi-static events. And this basically allows you to linearly superimpose results via user-defined functions. So this is really a powerful tool in and of itself. But what happens with TrueLoad is you're going to collect time histories of loading from the strain data. So we'll calculate time histories of loading that map back to individual result sets in your FEA model. And then TrueQSE is the tool that allows you to fully visualize and fully realize the full field results on your model. So TrueQSE is so important for understanding your loading and your loading response. Whenever you get TrueLoad, we automatically bundle in TrueQSE along with the product. Okay. And the third product we've got is a fantastic product we called TrueLDE, and LDE stands for Linear Dynamic Events. And this is a purely analytical tool. It works with your linear dynamic solutions in the time, frequency, and PSD domain, and it's super powerful. It has got lots of capabilities. It allows you to convert your results between time, frequency, and PSD domains. You can query any node or element on your structure for any response you want. You can generate operating deflection shapes. And an extra added benefit that you get from TrueLDE is that when you set up your models for use with TrueLDE, your linear dynamic solutions end up running 90% faster. So when you buy TrueLDE, we basically bought you a supercomputer for doing a linear dynamic response. So it's a super powerful tool that allows you to explore that. We won't go into the depths of TrueLDE today, but just to let you know it's there. And then since we're so concerned about getting the loads right on your products, we know when you're doing FEA-based fatigue, the biggest unknown for doing FEA-based fatigue is the loading. So we've got natural interfaces to the major FEA-based fatigue tools out there, so that if you're doing FEA-based fatigue, you can use our products to basically set up your run decks for your fatigue softwares and then run your FEA fatigue analysis as part of your normal workflow. So really it becomes a button click to run your FEA-based fatigue software, whereas if you didn't use our tool, it would be taking a half a day or a day out to set up your job. But now with a button click, you get everything set up to run your FEA-based fatigue tool as well. So you don't need to have FEA-based fatigue to use our software, but if you do, it makes it running the software easy and efficient. So Just a little elevator speech with TrueLoad. This is the only tool that you can use FEA and test to understand all of your product loading. And this is just what we do. We're helping our users understand their full field product loading so they can do proper analysis with the great analysis tools they've got. So the motivation behind TrueLoad is quite simply, what's the load? So if you're a design engineer that has to design products, components for this motorcycle, but the loading is crazy nonlinear, and you can't measure the loads, you can't simulate the loads, but you as the design engineer need to use loads to do design simulation to make sure the parts function and are durable. Well, what do? Well, we recognize that the individual components of this motorcycle are basically responding linearly. So we're going to put strain gauges on the swing arm, the crankcase, the frame, the handlebars, the fuel system, the luggage system, the fenders. We'll put strain gauges in all of the subsystems of this motorcycle, but the subsystems become their own load transducers. And then we'll get operating loads for these subsystems to use for design and optimization, okay? So this is a really great and powerful tool and allows us to fully understand all the loading on this motorcycle. Even though the loading is very nonlinear, the response to the components is linear. This is based on a technology called influence coefficients. Influence coefficients have been around for about 50 years or so. The problem with them historically have been is that it's all been experimentally done. So you had to guess where to place strain gauges, you'd guess at a correlation matrix, you'd have a poor correlation matrix and poor results. So it never quite caught on. And what we have done, we have optimized the gauge placement and the correlation matrix. So you've got the best correlation matrix, the best gauge placement, so that the results you get from TrueLoad are the actual operating loads, so you can use it for your design and durability work. So TrueLoad is all based on linear systems and loads, okay? So linear system is where loads are proportional displacements, displacements are proportional strains, strains are proportional loads. It's a linear system. Now we fully realize everything in life is nonlinear, okay? We understand everything is nonlinear, but we're turning your product into a load transducer. So we're going to target nominal areas of the product for strain gauge placement. So we're going to stay away from areas of high stress concentrations. So we'll stay away from welds, we'll stay away from bolted joints, we'll stay away from areas of contact. We're going to be in nice nominal areas where we're going to place the strain gauges, where the strain response is going to remain proportional and linear to the exterior loading. The exterior loading can be as nonlinear as anything. It could be ramp loading, sinusoidal loading, impact loading. That doesn't matter. We just need that strain response to remain linear and proportional to the exterior loading. So I can take this little diagram here and turn it into a couple of equations, okay? So the right-hand side, well, this is just Hooke's law, F equals Kx. So if your structure is obeying Hooke's law on bulk, you can have local plasticity, but if on bulk your structure is obeying Hooke's law, then the left-hand side of the triangle has got to work as well. So this will be strain times a correlation matrix is equal to load. And we're going to calculate load as strains from test times a correlation matrix from FEA, okay? This is essentially what we're doing. We're turning your part into a load transducer. And so this is a very powerful tool. And this equation here is known as influence coefficients. If you looked it up in the literature, you'd find this equation all over the place. Okay, just going to take one little segue here for a second here. As engineers, we are often drawn to putting strain gauges in hot spots, okay? And I want to show you the fallacy in that here. So here we've got the classic notch plate here. And the notch plate's got a nice little hot spot there at the tip of the crack. And so if we had an axial load on the plate and a shear load on the plate, if we place great gauges at the hot spot, we couldn't separate out those two loads because the hot spot's always going to be hot no matter what the load is. So the strategy with TrueLoad, what we're going to be doing is we're going to put gauges in nominal areas here. The nominal strain response in these areas here will be proportional to the exterior loading, and we'll be able to use these for loads. And then by all means, if you've got durability work that you want to do, I want you to place gauges here in the hot spots. That's important. but we can't use these for doing load correlation, for calculating loads. But we can use these gauges to calculate loads with true load, and these are the gauges for your durability work. And the true load tool has got all sorts of great tools for allowing you to allow both true load sensing gauges and these gauges in hotspots, which we call gauges of interest. So this is a very powerful tool, and we want you to do this, but just remember that you need to have gauges in nominal areas in order to calculate your loads. Okay, we're going to go through a series of examples here. Okay, we've probably got 4 examples or so here. This first one is one of my favorites. It's one we did with some college students at the University of Wisconsin-Milwaukee. At Wolfstar Technologies, we hire interns from the college, and it just so happened the one year I hired an intern, he was a graduate student, and he happened to be the captain of the SAE Baja car team. So he said, "Hey, Tim, we want to use your software to help us measure the loads in our suspension so we can redesign it." So working with this young person and his team, we basically set up an FEA model to have a series of unit loads on it. So we put unit loads at the shock, unit loads at the center of the wheel, unit loads at the top and bottom of the stabilizer struts. So we had about 11 unit load cases on this swing arm here, and we set it up and ran it through the FEA solver. And then this is what the unit load response was for all of these unit load cases. So this is just unit loads, okay? These are not the actual loads, these are unit load cases. And now that we've got that, then the true load software looks at the strain response in all these unit load cases and comes up with the optimal strain gauge placement here. And what's very interesting about this is that you see we get some strain gauges laid up here on the arm, but most of the strain gauges end up being on this forging. And that makes sense because the load paths are all, we've got these 3 sets of unit loads on this forging here. So we need to separate each individual load path, and the forging ends up being where most of the load paths go. But we do have some load paths on the arm here. So we have these 16 or so unit strain gauges laid on the arm, and then these students went off and did it. Now, the person working for me was a graduate student who's working on his master's degree, and there was 2 undergraduates on this team. So I had these 3 college students, and these guys had FEA in school, but it was just FEA in school. They had never built a real working FEA model for practical problem. So I coached them on how to set up the FEA model for this problem. And these students had never touched a strain gauge, okay? They had never had any opportunity to lay strain gauges on structures. They had never done any data collection or anything. And so you had these three students here. They were able to go from knowing absolutely nothing to completing this project in 6 weeks. So you can see they did a very nice job with laying the strain gauges on everything, instrumenting up all the data collection systems, and they even went as far as building a jump. So they built a jump here, and we're collecting data over this. And so we actually turned the parking structure at the university into our proving ground. So we're collecting data over this jump, and we also did max brakes and hard turns going up and down the ramps. So we collected some really good data in this parking structure here. And what you're going to see now from this data we're collecting going over this jump here, this actual data here for this very jump here, we'll see on the next screen here, okay? So these green curves on the left, these are the time histories of strain for our Baja car going over that jump, okay? So we've got these strains going over the jump, and then we take these strains now, we multiply them by our correlation matrix, and this now outputs a time history of loading. So these are all of our 11 unit load cases and how they're fluctuating as it goes over that jump. And then what TrueLoad does automatically in the post-test process, now that we've got the measured loads, TrueLoad automatically goes back into the FEA model and pulls out simulated strains and plots the simulated strains up in blue. So the green curves, these are measured strains, and the blue curves, these are simulated strains at the gauges. And then we do a cross plot. On the bottom is a cross plot. This is showing measured strain versus simulated strain for all of our strain gauges. And look at that, we've got nearly 1-to-1 strain correlation. I would challenge any automotive manufacturer out there to show me a strain correlation plot that good, okay? And this was just 3 college students not really knowing what they're doing and getting it all done in 6 weeks. This is pretty incredible stuff. And then of course, once we've got the operating loads in the structure, we can generate an operating deflection shape. So this is fantastic. They got great correlation here. They could see the loads on the structure, but what these students really wanted to do is they really wanted to do redesign. So they made up a duty cycle here. They said, okay, a typical race course would have 30 hard brakes, 40 hard turns, 20 jumps. And so when they put that all together, that was about 5.6 hours of time for one duty cycle. We ran that duty cycle through the fatigue software. The fatigue software was saying that that could repeat 278,000 times. So they were way over designed. And so through just doing some very simple FEA changes here, all they did is they went in and they thinned up the shell properties for the FEA model, and they went through trial and error here and thinned up the tube properties here. And by the end of the week, they had taken 25% of the weight out, and now they were still over designed. They still had 12,000 repeats. It's more than they needed. So they had plenty of safety here. And basically what happened here is they were able to thin up all of the tubes, except for this one diagonal tube had to stay the same. So through this effort here, they were able to take out 25% of the weight. And then my charge to these students for doing this project is that they had to write an SAE paper and publish the SAE paper. So there's actually a peer-reviewed SAE paper out there, and you can get this off of our website if you'd like, and download it. Okay, so this is a great little project these students did, and just showing how inside of a week you can do 25% redesign very quickly and easily based on real data. So this is another project that I've had fun with this year. Since we've all kind of gone through this period now with COVID and the lockdown and everything, one of the things that my wife and I decided to do is buy a camper so we could get out of the house and see the world. And so this is a picture of our camper and our Toyota RAV4 here. And one of the curiosities I had is like, wow, this camper is putting a lot of load on my trailer hitch in my car. I'm curious what those loads are. So since I can do this, I would often did this. So I basically set up an FEA model of my trailer hitch here. So I put unit loads X, Y, and Z. And I'm sorry I didn't use automotive coordinate system. So X is lateral, Y is vertical, and Z is fore aft. So I've got unit loads here on my trailer hitch. And now that I've got these unit loads, then I can go into my TrueLoad software, and the TrueLoad software said to place strain gauges here. So we're placing 6 strain gauges on the structure. So I've got 2 gauges on the back here, and then 2 gauges on each side, like on left and right side there. So I had my 6 strain gauges I've set up with my TrueLoad software, and I've got this great correlation matrix now. And now I can just go off, and I instrumented up my trailer hitch, and I hooked it up to my car here. So you can see I've got the strain gauges all mounted up and everything wired up, and we've collected strain data. So this is me driving down the highway, I believe, of strain data. So this is my 6 channels of strain data, and everything seems to be working nicely here. And now that I've got the strain data, then TrueLoad will then just take that now and we turn this into loading. So here on the left-hand side, I've got my 6 channels of measured strain data in green. We multiply that by the correlation matrix, and now this outputs time histories of loading, FX, FY, and FZ for my event here. And then again, like I showed before, now that we've got the loads, then TrueLoad automatically goes into the FEA model and pulls out simulated strains of the gauges and plot those up in blue. So the green curves are measured, the blue are simulated, and we got the measured strain versus simulated strain cross plot, and we're getting excellent correlation here. Okay. So now I've got great confidence in my loading, and I can even go off and generate the operating deflection shape for my trailer hitch. Okay, so now I can see what loads are happening on my trailer hitch as I'm pulling my trailer down the highway. Okay. So what's interesting here, I got a very unexpected result. Okay, so if we take a look at these time histories of loads here, okay, the blue curve, well, that's the FX. So that's the lateral load, and that's happening right at around 0 here. Okay, but now if we take a look now, the FY load, the FZ load case now is the green. So take a look at Z. So that's the 4F load case on my structure here, and that seems, you know, pretty decent. That seems like a normal type of load cases here. So FZ is positive going forward, so I'm getting a lot of negative loading. So that makes sense. That's the right pull direction, right? And then the FY load. Okay, so this is the counterintuitive piece here, right? Because, you know, all of us from our mechanical engineering, when we'd sit down and do a load calculation on this trailer hitch, we'd look at the CG of the trailer, gravity, and we'd calculate a downward load on the trailer hitch. And there is downward load on the trailer hitch, but what's happening is we're getting a lot of upward load. And the problem is that we've got, as I'm going down the highway, I'm getting a lot of aerodynamic loading on this trailer. You know, it's basically like pulling a big sheet of plywood through the air, and I'm getting all this aerodynamic loading on it, and it's causing this trailer to push backwards and lift up the trailer hitch. So there's a lot of unexpected upward loading on my trailer hitch, which I would have never thought of. So this is a very interesting result. Okay. All right. This is from a customer, C&H. They make these front end loader systems for heavy equipment. And part of C&H's signature design is this thing that they call the H-link. Okay, so this is a very important feature. And they were designing a new series of their front-end loader system, and they started off with a new design. So the engineer at C&H wanted to understand the loading on the system as they developed the new system. So what they did is they looked at all the pins here on this H-link, and they basically put X, Y, Z loads and Y and Z moments on the or X and Y moments on each link. So they had 5 degrees of freedom of loading. They ran this with inertia relief. So they had 20 unit load cases on the structure, and TrueLoad told them to place about 32 strain gauges here. So you see the 32 strain gauges distributed around the structure. And then they took it to the proving grounds and did testing. And what you see down below here, this is the cross plot like we've been seeing before, where we've got measured strain versus simulated strain for all 32 channels of data here. So this is all 32 channels of data on this customer's product, and they are nearly 1-to-1 strain correlation. So they had excellent strain data. So they felt really good that they were able to understand the loading on this. Now, as it turns out, their initial design had some durability issues. So that right away they had some durability issues. So what you see on the left here is there's this little blue area here. The blue area is showing low life. So they're having very low life here in the stress concentration on this H-link. And so what they did is they put a strain gauge right in that stress concentration in real life. And then they also went into our True QSE tool to query that same location. So what you see up above here is the red curve here. This is their measured strain data at that location. And the blue curve is the simulated strain coming out of TrueLoad. Okay. So they had excellent strain correlation, even in this hot spot, even though it was far away from where they had any strain gauges laid for load reconstruction. So now that we've got this really excellent strain correlation here, they drove these loads into their durability tool, and then they went through a series of durability redesigns, and so they came up with the a series of redesigns, and this is probably, redesign effort, 3 or 4 here, where they actually came up with a side plate here that was able to take away that stress concentration. And, within a week, they had a design that was working, and they had high confidence this design was going to be right. Okay. The paper for this is also on our website, so if you want to download the paper, you can go ahead and do that too. All right. And I believe this is our final example here. This is our customer Aaron's up from Brillion, Wisconsin, just a couple hours north of Wolfstar headquarters. And so Aaron's makes these very high-end lawn and garden tractors, these zero turning radius mowers. And we came up and visited them one day, and they were showing us that they had this design problem on their engine deck. Basically, the engine deck, it supports the engine and transmission, and it sits under the seat on this tractor here. And the system was basically working fine for them, but their transmission supplier wanted them to open up some airflow to help cool down the transmission. So they reached out to us to see if we could help them with that redesign effort. So working with them, we decided to treat the system as a basic citation problem, because basically the engine and transmission are basically sitting on this engine deck, and then the whole system is being bounced across their proving grounds. So they thought that this was fair to treat this as a basic citation problem. So our unit load cases were 10 Gs, X, Y, and Z. So you can see the response there for each of the unit load cases. And you can see where true load said to place strain gauges. So true load said to place 8 strain gauges on the structure here. So we place 8 strain gauges on the engine deck here. And now that we've got these 8 strain gauges laid, we just went to the proving grounds. So up on the top left here, this is the time history of all 8 strain gauges. So we took this 8 strain gauge time history from their proving grounds. We brought that into true load. True load calculated the operating loads. And then once we had the operating loads, true load went in and back calculated the simulated strains at the gauges. So we've got the green curves are measured strains, and the blue curves are simulated strains. They're line on line. You can't see the blue curves, right? And down below is our measured strain versus simulated strain. It doesn't get any better than this. Look at this perfect one-to-one correlation here, okay? Now that we've got that, we can generate the operating deflection shapes. So this was great. We had really great correlation with the system, but and we were starting to get ready to go on this. But one of their engineers had started redesigning this engine deck already, because Aaron's is a very robust engineering organization. They actually had design guides for engine decks, and so the design engineer basically sat down with the design guide, set up his FEA models, and did his first iteration. And he was pretty happy with what he had come up with. And they actually had his first iteration on test, and they wanted to show it to us on test. And they brought us down to show it to us in the lab. And when they took us down there to the lab, it was on the shaker test. They went to show it to us, and it had failed about an hour before we got there. And I believe the system failed in about 1,200 hours, and it's supposed to go 10,000 hours. And so this is their first iteration of design. You can see they got some high stress concentrations up here. And I said, perfect, give me that FEA model. Let me run the loads in the FEA model, and let's see what's going on. And then and I'm going to show you durability plots in the next slide here. But then working with the engineers, we came up with a different pattern here. So we came up with a new hole pattern here on the system. So we had 2 large holes, and our initial design, we had 2 layers of sheet metal, and they were riveted together, okay? And we were really happy with this. We thought this was a really good design. The manufacturing engineers hated us. And so we had to go back and take our 2 layers of sheet metal and get it back down to 1 layer of sheet metal. So then we iterated on thicknesses of sheet metal, and by the end of the week, we had a design that worked. So let me show you what's going on here. So this is the durability calculations here, okay? So their goal for this was 10,000 hours, okay? So the yellow here is showing the 10,000 hours on their material curve. And so we really want to see yellow, green, and blue in these plots. We don't want to see any red. And so their baseline design was fine. There's some red here because of the RBEs we've got in the structure, but really their baseline design was just fine. And then this was their first iteration. Well, after we ran the loads through it, the durability software is telling us that the structure is going to crack right through here. And that is where the structure cracked. And the durability software said 1,000 hours, and it actually cracked in 1,200 hours. So this is perfect correlation for fatigue. So we had excellent results here. And then working with the engineers and the new designs, we had much better durability results. And so by the end of the week, we had a design that met their airflow needs and met their durability needs. And we did this all in like 8 days. So this is, pretty incredibly quick. Okay. And in talking to the engineers at Aaron's, we said, hey, if you had done this without TrueLoad, how would this go? And they said, well, each time we do a prototype, it costs us about $30,000 to prototype and test the parts. It takes us about 6 weeks to procure the parts, and we're guessing at in between each design iteration. So if we did 5 design iterations here, that would have been 150 grand in 30 weeks. But with TrueLoad, we basically did this all in 8 days. And if you amortize the cost of TrueLoad, you're down to $2,000 in 8 days. $2,000 in 8 days versus 150 grand in 30 weeks. This is really the type of results our customers see, and this is the real value add that TrueLoad brings. So, really just to summarize things here, with TrueLoad, we can give you a tool that will give you optimal strain gauge placement. You'll get unprecedented correlation. Strain correlated load time histories. You'll get to reduce your test costs and your analysis costs because you're using correlated loads. And you get the true knowledge of the operating loads in the structure. And you end up saving huge amounts of money because you're eliminating entire iteration cycles, entire build test iteration cycles out of your product development methodology. So we have got tons of great features I didn't even get into: sliding loads, hybrid loading, contact control, embedded solutions, and more and more and more. I'd love to go into full details with that. Please reach out to your folks at EngineSoft. We'd be happy to work with you and show you all the great features that we've got in the TrueLoad software. And with that, I think I'm out. So thank you very much. If you've got any questions, we'd be happy to take that now. Let's take a look at see what we have here.